Hi, my name is Akseli Manninen and I'm presenting my thesis on spatiotemporal traffic accident prediction using deep learning models. This presentation starts by introduction, giving also a short overview on the related studies. Then problem statement is explained, and after that data and models are described, and then the results of the experiments are discussed, and finally conclusions are provided. Every year, approximately 1.19 million people lose their lives in traffic accidents, and these accidents are the primary cause of death for individuals aged 5 to 29 years. Multinational organizations such as the European Union have set ambitious targets to reduce these accidents. And in Helsinki, where this study is focused, similar goals are set to halve the number of accidents by 2030 from the baseline of 2020. Accurate predictions of the accident locations and times could help to prevent them, and in the field of traffic accident prediction, deep learning models have demonstrated superior performance. Therefore, this approach is taken in this thesis to predict the accidents. Traffic accident prediction is a wide field of study, and this thesis focuses on its subfield of spatiotemporal traffic accident prediction with deep learning. Within this subfield, various prediction tasks exist related to, for instance, classification and regression tasks, and different ways of quantifying accident risk and utilizing different spatiotemporal resolution. And different models are applied in the field. Some of the most popular ones in deep learning are recurrent neural network-based models, convolutional-based models, graph-based models, transformer-based models, and often in the studies of the field, these models are combined together for improved predictions. So the study area is Helsinki, and the study period is from 2019 to 2022. As preliminary information, the area of Helsinki and the study period are divided spatiotemporally. The area is divided, as can be seen on the right, to grid cells of size 1 kilometer times 1 kilometer. This grid net can be considered as a matrix, and we can observe values of different sorts for these grid cells, which corresponds to cells of a matrix. And these grid nets are so that we can for different time steps have different matrices, and hence the spatiotemporal aspect. So given a sequence of observations from past 7 days, where 1 day corresponds to 1 time step, predict the number of traffic accidents in each of these grid cells for the following 7 days. This is illustrated at the bottom. So the observations are a sequence, and then we are getting one total output for the following period of 7 days. The research questions are the following. Among the implemented models, which ones demonstrate the highest performance in traffic accident prediction in terms of the evaluation criteria? Second, which groups of features have the highest impact in improving the predictions of each model? And third, are the traffic accident predictions aligning with the real world constraints? Next, the data collection process. The data is collected for years from 2019 to 2022, as already explained, from various data sources such as application programming interfaces and directly downloading data from websites. Optimally, we would use data that would extend to 2023, which is in Helsinki the first year without the restrictions of COVID-19, but this data is not yet available for traffic accidents. Data is mapped by date and location. For instance, the traffic accidents are mapped based on the accident date and the coordinates of the accidents into grid cells. And 17 variables in total are established, including traffic events, calendar features, weather information, and map data. And these are divided into training, validation, and testing data sets. The process of extracting other features is already a little bit discussed, but for map data, the process is a little bit different. So maps are retrieved in a map software through a web feature service. You can see an example on right for paved road network, and then maps are cropped into submaps using the coordinates of the grid cells. And this is displayed on right for a single grid cell. And from these submap images, the number of pixels are used as the features. So for instance, in this case, we would get the number of red pixels for that image to represent the extent of paved road network within that grid cell. Moving on to models. In this study, 4 models are used: long short-term memory, LSTM for short, convolutional neural network LSTM, CNN LSTM for short, transformer, and historical average. The 3 first are deep learning models, and the 4th one is a simple baseline model. As a preliminary information for the models, they all use, or all of the deep learning models use this road network grid mask, which is created to improve the predictions. So as can be seen, Helsinki is partly covered by the sea, especially in the south. So to improve the predictions, the deep learning models use this mask as a layer to multiply the predictions of the model by 1 if they are included in this mask, and by 0 if they are excluded from this mask. This mask is created using the paved and dirt road networks. So if the grid cell contains any roads, it's included here. First of the models, LSTM is illustrated on left. It uses 2 inputs for time variant features, which are, for instance, the weekdays, and time invariant features, which are, for instance, the roads which do not change within the observation period. 4 LSTM layers are used, and then these features are merged together, and then they are processed by fully connected layers, and finally by the road network grid mask to make the prediction. The LSTM memory cell, which uses different gates and activation functions and so on, is illustrated on right. So this is what is happening in the LSTM layer. And one thing to know about this model is that it makes predictions for a specific grid cell at the time. So it takes a sequence of observations for a single grid cell and then predicts the accidents for the next week for that grid cell. Moving on to CNN LSTM, this one also has two inputs, but this time for space variant features such as, again, the roads, and then space invariant features such as calendar features. And the first category is processed by the CNN, which this time takes in a sequence of matrices, so different from LSTM. So this time the input is for all of the grid cells at once. And so this can be considered as image prediction task. And these are processed by CNN and then reshaped to be applicable for LSTM, and then these different features are connected together using Hadamard product and then processed by fully connected layer and grid mask. So, and this time the prediction is made for all of the grid cells at once. Then the transformer model, this works in regards to the prediction task similarly as LSTM. So this time it takes one input sequence for a specific grid cell, then process it using fully connected layer, then in transformer positional encoding is used to maintain the information of to which time step does this data correspond to, which is necessary for this model because it doesn't have, for instance, similar structures as in LSTM to give this information otherwise. Then to the encoder layer, there are 3 stacked encoder layers, and these are illustrated on right as transformers in general. This one is based on attention mechanism, and it's included in the encoder structure, which also includes feed-forward network. And these are applied to the after positional encoding, and then they are reshaped for fully connected layer, and finally grid mask is used to make prediction. And as said, this is making prediction for a single grid cell at once. This is quite simple transformer model due to limited computational resources. And there are other transformer models for traffic accident prediction introduced in related studies, but they are usually using only one or a few features, whereas in this study we are using 16 variables to make predictions, so those models would need much work to be extended, and they are not within the scope of the resources of this thesis. So therefore this lighter and simpler transformer model is used. Finally, historical average, it's calculated individually for each grid cell using the training data. So for each period of 7 days for each grid cell, it calculates the total number of accidents and then takes the average over the periods. One thing to note is that different days can be used in multiple windows, as the window is always lighted by one time step or one day to produce the next window. Then a little bit about the training configuration. The loss function used with the models is mean squared error, MSE loss for short, which is used also in many of the related studies. Similarly, the optimizer is selected based on related studies, and we are using RMS prop, which stands for root mean square propagation. And 100 training epochs are used, and early stopping is employed after 5 epochs if the results are not improving with the validation dataset. Then to results and numerical evaluation. In this thesis, 3 evaluation criterion are used. MSE, then mean absolute error, and recall. In this study, the recall is calculated such that when accidents occur in a period, they form a set of grid cells, and then they are compared to a set of same size of the grid cells associated with the highest risk predicted by the models, and then it's compared how many of these are shared together. And this is used in multiple related studies. So it's about identifying the regions with the highest accident risk. And so in this evaluation, CN and LSTM performed the best among the models in terms of MSE and recall, while LSTM performed the best in terms of mean absolute error. Something to note also is that CN and LSTM achieved robust results also with fewer features. So the features were divided into groups, and these groups are added increasingly to assess the impact of these groups on the predictions. So with CN and LSTM, especially in terms of recall, it performed well compared to the other 2 deep learning models. And for those models, when adding feature group R, which includes the road network information, their recall also improved a lot. So for them, this feature group seems to be quite impactful. Also, the model predictions were assessed visually for one week case study. So this period was selected based on high accident rate, and on the left you can see the real accidents, and on the right you can see the predictions made by each model in a heat map visualization. This case study reveals the differences between models that are not visible in the numerical evaluation. For instance, that LSTM predicts 0 accidents in many grid cells within the borders of Helsinki, whereas, for instance, transformer and historical average predict some accident risk on those. Also, it shows that the models were able to identify the elevated risk in the southern part of Helsinki, corresponding roughly to the city center, where accidents actually happened. And this also displays that accidents are predicted to within the borders of Helsinki and in places where they could potentially happen, meaning that they are predicting where there are roads. But it's also visible in this that the more scattered, maybe more random accidents were difficult to predict for the models. Finally, to conclusions, deep learning models are capable of predicting traffic accidents in the study area of Helsinki, with CNN LSTM performing the best overall. Different groups of features improve the predictions with different models, and in general, adding features adds the quality of the predictions. CNN LSTM is capable of predicting accidents with fewer features. The deep learning models are able to make sensible predictions, predicting non-negative accident risk, predicting accidents to regions with roads, and predicting the accidents within the borders of the study area, and predicting that accidents overall happen. These predictions could be used to implement preventive measures and to raise alertness of road users in order to prevent accidents and contribute to the goals of Helsinki. This approach could also be used in similar urban areas such as neighboring cities of Helsinki.